Blinded by the light, wrapped up like a douche, another runner in the night. Blinded by the light, wrapped up like a douche, another runner in the night. Blinded by the light.
So here we have the Bunsen burner flame, and if you look in your lab handout, you'll see there's about 10 chemicals that we're going to do in the flame test. It'll be your job to put the formula of the chemical, the positive ion, the negative ion, and then describe the flame color. So the first one, and I'll do these in the order that they appear on the worksheet. So the first one is sodium nitrate. I'm going to stick a wooden splint that's been soaked in sodium nitrate solution in, and there's our flame color. Okay, I'll do it again. You can write down any way you want the color. I keep it to orange, orange-yellow. If you want to pretend you work for the J. Crew catalog and call it clementine or tangerine, you go right ahead. Next up is sodium chloride. So first was sodium nitrate. This is sodium chloride. And you notice, well, you'll notice what you notice. And then you might wonder, well, why did you show us two with the same? Well, one of the early questions you're going to be asked is it the positive or the negative ion that's responsible for the color? So this will help give you some information so you can not only give an answer but justify it. Next up, we have potassium nitrate. Here we go. Now we're going to do potassium chloride. Next up, copper 2 chloride. Next is lithium chloride. Next is calcium chloride. And you might notice sometimes it can be hard to tell some of these apart from each other. So when you get to your unknown, it might be you can't tell perfectly. Here's some barium chloride. Strontium chloride. And last, for the knowns, cesium chloride. And then you have an unknown, and your job will be to give your best answer as to what you think the unknown is. If you can tell with some certainty, say so. If you can only narrow it down, that's okay too. So here's your unknown. And that completes the flame test portion. So what I have here are some what are called UV detecting beads. So these are plastic beads that have embedded in them a variety of chemicals that can absorb light at one wavelength and emit light at a different wavelength. And what we're going to do is we're going to shine ultraviolet light on them with this little UV flashlight, and we'll see what happens. Now, right now, these beads are essentially getting only visible light. They're getting Roy G. Biv. And so they just have a milky white color. So let's turn the flashlight on. And I think what you'll notice fairly quickly is that we're getting color changes. And what's happening is the beads have absorbed the UV light, which has a shorter wavelength, a higher frequency, and a greater energy, and then they're emitting visible light. So they're absorbing light of one energy and emitting light of another. And when the light's all gone, when the light's been emitted, the energy's kind of given back, they'll return to their whitish color. So you can see some of the beads are turning. Now, these beads just come in a pile with a bunch of different chemicals. So here's an example, this is kind of an example of that. You may have seen some shirts that when you go out in the sun, an image appears. Those shirts are treated with some of the same chemicals. They absorb the small amount of UV light from the sun. That's why mom tells you to wear sunscreen. And they emit visible light. Okay? It could not go in the other direction. And you probably get asked that on a worksheet. And you want to think about why it's not possible for something to absorb one amount of energy and emit a greater amount of energy. So what I have here are a few samples of fluorescent minerals. So these are going to be a little bit like the UV beads. So right now this is kind of just an unimpressive rock. I'm going to shine my ultraviolet light on it and we'll see what happens. I don't know if you can see, but there's kind of a yellow color down at the bottom and a purple color. Let me go to the next one. Here's the mineral. I shine the UV light on it and you could see some pink, purple light being given off. And the third one, give it the UV light, and you get completely different colors. So this is absorbing higher energy ultraviolet light and emitting lower energy visible light. If it didn't emit visible light, it probably wouldn't be much sense of my showing it to you. So what I have here is a spectrum tube, and I know it's a little hard to see right now, which is a tube filled with, in this case, hydrogen gas that I'm going to send an electric current through. So in the flame test lab, we energize the electrons of the atoms by using heat energy to make them move between energy levels. Here, we're going to use another form of energy, electricity. But what's going to happen is the electrons are going to be energized, move from lower to higher energy levels, and then when they return back to what's called the ground state, they're going to emit that energy. Now the first thing we're going to do is we're going to run through our 6 samples and you're just going to notice the general colors. Then we'll see if we can analyze them in a little more detail. So first up, hydrogen. Next, helium. You might notice it's a different color. Next up, neon. And that might remind you of neon lights because that's exactly how this is done. And neon lights are not all neon. Next up, I've got argon. Next up, I've got krypton. And last, I have chlorine gas. So Well, a lot of them were in fact noble gases. They don't have to be. You may have noticed street lights have different colors, or lights people have outside their home. Some have a bluish tint, some have a yellowish tint. That's exactly what's going on. So now what I'm going to do is I'm going to go back to my helium tube, and I'm going to turn it on, and we're going to just observe that it has kind of a faint pinkish purpley color. Now I'm going to place in front of it what's called a diffraction grating. This is a piece of plastic that has about 10,000 lines etched on it every inch, and it's going to act like a bunch of prisms. So let's see what happens when I put this in front. And let's try it this way. And what you notice is, off to the side you see a bunch of lines. So there's a red, there's an orange, there's a couple greenish and a violet. And each of those lines is caused by specific energy transitions. Now, when they all come together, hit our eye, and signals go back to our brain, we kind of do an averaging. So if you look at that, there's not much clue looking at it without the grating that there's green light that's part of that. But there is. And by analyzing the light that comes out of something, we can figure out what's in it. So that set of lines that you're seeing is unique to helium. So if I do this to a star, I don't mean Kardashian star, and I see a specific set of what are called spectral lines, I can figure out what elements are in that star. Because obviously we haven't gone to the stars, we haven't gone to the sun, taken a piece of it, and analyzed it. And that is, in fact, how we know what the stars are made of. We have a lot of telescopes that are not just looking at visible light. That is also giving off UV light, can't see it, infrared light. Stars give off radio waves, microwaves, and while they're not visible to our eye, they can be detected. And a lot of the telescopes that are pointed at various things in the universe are looking at the energy, the wavelength, or the frequency of what's being emitted, and we use that to try and figure out what's going on in the stars and how the universe was created. So what I have here is kind of a model for what was going on in the flame tests, the spectrum tubes. It's kind of a quantum ladder. So usually when you have described to you energy levels, they're presented as concentric circles or spheres, which is a pretty good way to do it. I think this ladder might be another way, and maybe it'll help things make sense. So the key is that when we talk about energy in atoms, it's primarily determined by the distance from the nucleus. So the first energy level is fairly close, second, third, fourth. Here, it's going to be distance to the ground. And it is a kind of potential energy. And you probably have learned about potential energy as being like height. Well, that's gravitational potential energy, but it's the same idea. So as we go up this ladder, things are getting farther away from the nucleus, and they have a greater energy. You'll notice the spacing is not like a normal ladder because the energy levels in atoms are not spaced evenly. The distance from the first to the second is much, much larger from say like the fifth to the sixth. And when you get up much above here, there's almost an overlap. Because remember, energy levels aren't boards. They're not even physical things. They're descriptions mathematically of distances. And they're clouds is how we describe them. So if you think about a cloud, it doesn't have a definite start and stop. So there's actually some overlap. And when you learn to do configurations and things like that, that'll account for some of the exceptions. So When an electron absorbs energy, heat, light, electricity, it goes from what we call its ground state, its lowest energy, or its preferred energy if you want, to a higher level. That's called an excited state. So for any atom, there's one ground state. That's the lowest energy preferred arrangement of electrons. There are multiple excited states because any arrangement of electrons with a greater energy than the ground state is an excited state. So there's not like a more excited state or anything like that. When those electrons are energized and are at higher energy levels, they, quote, don't want to be there. They come back to their ground state. And when they do, they give off or emit that energy. And if you think about the electromagnetic spectrum, there's a whole range of energies. What we did was we dealt with energies that were in the visible spectrum, Roy G. Biv. So, for example, an electron moving from energy level 6 back to energy level 2 might emit blue light. An electron going from 4 to 2, which is a lower amount of energy, lower frequency, higher wavelength, might emit green light, orange, red, etc. And you might ask, where's the purple? It's well, for one thing, I don't have purple tape. And this is the kind of the model for the hydrogen atom, which only has one electron. If there are more than one electron in an atom, which is obviously the case for all the others, it's much more complicated. The math is almost impossible to do, but the idea is pretty much the same. So what about these things here that look like saran wrap? What I was trying to do here is show you that, say an electron went from energy level 6 to energy level 1. That's much more energy than blue. And it turns out that would fall in the range of ultraviolet light, which we can't see, hence the saran wrap. Going here from 6 to 5, this is a very small amount of energy. In fact, it's much less energy than red. You can almost see from the distance. That could be infrared or microwave or anything with the lower energy. Typically, things that fall or return to energy level 2 are in the visible range, to energy level 1 are in the UV range, and to energy level 3 are in the infrared range. So energize an electron, goes up, returns, and gives off light. Another thing is, it doesn't have to return in one step. So an electron that got energized to, say, energy level 7 could kind of fall back home in a series of steps, each of which would give off a different amount of light. The energies, the wavelengths, or the colors are unique to each atom. It's almost like an atomic fingerprint. So if I see, and we can take these, and even though that's red, it's not very difficult to analyze that and not just say it's red, but to say, oh, it's red with this wavelength or this frequency. And that's something that's we've been able to do for over 100, 150 years. So when we want to know what's in a star, we essentially point a telescope with a diffraction grating at a star. We look at the lines and we match them up to what's on Earth, because lithium atoms are the same throughout the universe.
You know that it would be untrue. You know that I would